Hello, everybody. Welcome to the Global Composite Expert webinar series. My name is Wenbin Yu, Director of Composite Design and Manufacturing Hub. This webinar series will examine the history, present capabilities, and future of composite science and technology, with the goal of sharing the knowledge of composites that has been developed over the past 50 years. This webinar series is initiated by the Composite Manufacturing and Simulation Center at Purdue University. We are located in this beautiful Indiana Manufacturing Institute. All of you are welcome to visit us when life returns to normal and we can travel safely. We launched the Composite Design Manufacturing Hub in 2013 with the mission to convene and serve the global composite community by creation, education, evaluation, and sharing of resources for composite design and manufacturing. CDM Hub provides a very powerful website called cdmhub.org for the global composite community to carry out this mission together. We envision CDM Hub to be the premier resource for composite design and manufacturing. This webinar series is one of the initiatives CDM Hub started as a service to the global composite community. This webinar series is made available by the support of CDM Hub sponsors, including Dassault Systems, Cytec Solvay, MSC Software, and Modex 3D. We greatly appreciate their financial support for CDM Hub. We invite more organizations to join us to support the mission of serving the global composite community. Next, I will show a brief commercial from one of our sponsors.
In case you are wondering, you are not fighting molding defects alone. Introducing Modex 3D, your plastic injection solution. With powerful molding simulation features, friendly and easy-to-use interface, Modex 3D pinpoints design problems before production and achieve better product quality with less time, less cost, and less waste. Modex 3D, the best partner for plastic industries.
This webinar will be recorded and made available on cdmhub.org. An email will be sent to all of you once the recorded video is available online. We have about 5 minutes for introduction, then the presentation will last about 40 minutes, and we'll have about 15 minutes for questions and answers. All attendees will be muted. Please submit your questions through the Q&A box. And after the presentation, your questions will be read and answered. Next, I will ask Dr. Byron Pipes to introduce our speaker today.
Welcome, everyone. Michael Wisnom is director of the Bristol Composites Institute, which builds on the work of the Advanced Composites Collaboration for Innovation in Science, ACCIS. We all know that he is a leading expert on the mechanics of fiber-reinforced composites, especially failure mechanisms and finite element analysis, with over 400 publications and papers. He's a member of the steering board of the National Composite Center, editor-in-chief and European editor for Applied Science and Manufacturing of the International Journal of Composites, Part A, a very powerful journal in our field. And he was director of the Rolls-Royce Composites University Technology Program from 2007 to 2017. He is a fellow of the Royal Academy of Engineering in the United Kingdom. And he is a fellow of the Institution of Mechanical Engineers and also of the American Society for Composites. Professor Wisnom was awarded a Royal Society Wolfson Research Merit Award in 2005 and was president of the International Committee on Composite Materials 2009 to 2011. He received the Medal of Excellence in Composite Materials from the University of Delaware, the Center for Composite Materials, and you all know that I was associated with that organization for some years as well. I'm delighted that Michael received that award. Professor Wisnom has a Bachelor of Science degree in mechanical engineering from Imperial College, one of the finest engineering schools in the world, a PhD from Bristol University, and after working in the British Aerospace Civil Aircraft Division in Hatfield, he joined SDRC Engineering Services as a finite element consultant, later as Technical Director, Europe. He joined the Aerospace Structures Department as a lecturer in aircraft structures in 1987, was appointed professor in 1995, and established the Bristol Composites Institute in 2006. We're delighted to have him as one of our expert lecturers.
Thank you very much, Byron, for the introduction and the invitation to be here. So I'm really pleased to have the opportunity to talk about what I think is this very important and very fundamental subject about strength of composites, and really asking the question, why haven't we made so much progress in all the years? There's still very many important challenges which we need to address. And this has really been the focus of much of my research, and I'm going to be bringing together things that I've learned over the years and trying to synthesize them into what I think is important. So the question is, why are there such huge variations in reported strengths? This slide here came from Hao Kui from Cranfield University and shows unidirectional compressive strength of IM 78552 from various publications. And you can see that the strengths vary by more than a factor of 2. So there's a huge variation in what's being measured. And the question really is why? So this was really highlighted by Dick Christensen in the paper a couple of years ago about why after 50 years are there still so many unresolved issues with measuring basic strengths. It's really a major reason for the lack of progress, I think, on failure of composites. And Dick Christensen commented that the data of these observed behaviors must be completely uncorrupted by the inadvertent and uncontrolled influences that almost inevitably creep in. So this is easy to say, but the way to avoid those problems is not so easy. And so the question I'm going to address this afternoon is, why is there such variation and what should we do about it? So some of the reasons for the differences, which I'm going to highlight, are first of all, I think there's an issue about language and about what we mean by strength and how we define it. There's also a whole issue about the test methods that are used, and also variations in how those tests are carried out. But perhaps more importantly, I think there are still factors which failure depends on that are not fully appreciated or fully understood. And I'm going to talk about some of those and try and highlight them. So first of all, let's talk about how is strength defined. There's lots of different ways you can define strength. If you do a test, you may get a load displacement graph, which may have quite a complex form. Do you define the strength as the first damage, the first fiber failure, the first load drop, when you get a reduction in stiffness, the load at the maximum displacement, the peak load, or just when the specimen completely disintegrates? Lots of potential definitions. Just to take an example of a test we did some years ago, you look at this stress strain curve, and at first sight, I think it's quite clear that the failure is here. But then if you look at it a bit more carefully, you see there's a little bit of a glitch there. Is that just some factor in the test? Is it significant or not? Might very easily be missed. But if you repeat the test, you see that it's very consistent. You see every one of these specimens has got a little load drop at a similar load. About 65% of the maximum tensile stress. It's very small, could easily be missed, and there's no obvious damage to the specimen. And in fact, it's able to withstand significant further tensile loading beyond that. But actually, delamination has occurred, and therefore, integrity of the specimen in further compressive loading will be compromised. So there's a question about which one we should take. Should we take that damage, or should we take the maximum stress? So the definition of strength is really quite an important point, I think, and failure and hence strength is really related to fitness for purpose. And this may vary substantially depending on the application. So if the main concern is the ultimate load carrying capacity, then damage may be acceptable. It can even increase the strength. The splitting that you get, for example, as a notch helps to blunt the stress concentration and can actually increase the ultimate strength. On the other hand, if you've got a tank and you're worried about leakage, then even one matrix crack may be problematic in giving rise to leakage. So I think the most important thing is that we must always define what we mean by failure. And you can't just read a report or a paper with no details and just take a value without really understanding what it means and where it came from. So this is an important topic. And recently I organized a workshop with Federico Paris from Seville on the topic of how do we define and measure strength of a composite. And we had a number of interesting presentations and a lot of discussion on that topic. And the videos are available on that website. And I think it was really quite interesting in getting a good discussion going about some of the fundamentals and what we mean and how we do measure strength. So at that workshop, we proposed a definition to say that the strength of a composite should be defined, or we proposed the definition that the strength of a unidirectional composite is the maximum stress the material can sustain under uniform uniaxial loading. So whilst you could have many other definitions, they are perhaps more subjective. And for example, damage detection depends on how closely you monitor the specimen. In the graph I just showed a bit earlier, you might very easily miss that point there. And in other tests, if you do very detailed in situ, SEM or CT during the test, then you might actually see the damage occurs even earlier. And in fact, possibly even before you've applied any load due to intrinsic defects or residual stresses. So-called intrinsic in situ strengths are even more problematic in my view because they depend on many other factors, as I'll perhaps highlight a few of them a bit later. So these different definitions may be useful in design, they may be useful for certain particular purposes, but if we're trying to get to the bottom of the basic material parameter, then I don't think that's really what we should be using. Now, if we do take that final ultimate strength as the parameter, then there may be considerable damage, but I think it's still valid as a measure of the ultimate material performance. And this can be applied to all the principal failure modes: tension, compression, both in the fiber direction and transverse and shear. And I guess what it really comes down to here is why do we want to define strength? Is it about getting the ultimate material performance? Or is it about, for example, values to go into a failure model? Or is it about design allowables? If you're worried about design allowables, then you've got to be conservative. But if you want to get to the ultimate strength, then you really need to understand and eliminate any premature failures. So test methods are problematic. I'm not going to say a lot about that because there's so much. You could have a whole talk or more just on the test methods. The real problem is that specimens tend to fail at the point of load introduction because you've got stress concentrations, you've got the presence of other stress components, you've got damage from the grips, potential excessive pressure. There have been hundreds and hundreds of thousands of studies published, and I think a lot of good work has been done. But what we're perhaps less good at doing is extracting what that means and trying to reach a consensus from all the work that's been done. Everybody's keen to do their own research, and actually synthesizing results that other people have done is not always such a popular topic, but I think it's actually very important. There's also a lot of variations in carrying out tests. So this graph here shows the results from a round robin, which was done with 7 major European laboratories, 7 different unidirectional carbon fiber epoxies, and this is plotting the compressive strength. And it's really very, very difficult to determine any trends from that data. There's so much scatter, again over a factor of about 2, and it's very hard to determine the trends of those different materials, which one is better than any other. However, if you replot that by lab rather than by material, you can see some definite trends. And in fact, the test lab, in this case, is having a greater effect than the material itself. And that's because the results are affected by details of the test method, specimen preparation, tabbing procedures, and other issues, clamping pressure, and other details of the test, which can have quite a big effect. Moving on then to factors which are not fully understood or appreciated. In unidirectional composites, volume of material tested is very important. The stress gradient can be important. And then there's also the effect of other stress components, defects, manufacturing variability. And then in laminates, you've got the issues because there are multiple failure modes that can interact. You've got the influence of other plies, and you've also got residual thermal stresses. So I'm going to look at a few of these factors and start off by talking about tension. So let's just talking about measuring tension strength. It's about the simplest thing you could want to do, but it turns out to be actually quite difficult. The problem is that the carbon epoxy is so strong that it fails where you grip it. Standard methods are affected by the stress concentrations, and that usually leads to premature failure. Now, you can overcome that by machining very gradual transitions, but generally you need to have very large radii, very gradual transitions, and the specimens need to be very long with a gradual transition. Another alternative way is to chamfer the plies. They can be chamfered either before or after curing. And the bottom picture shows some recent results where one of our students has developed a very nice way of chamfering the plies and can get very, very gradual transitions at the end of the plies. I think this is a very promising technique for the future, both not just for testing, but also for eliminating some of the delamination in practical structures. So with great care, you can eliminate grip failures, but it's quite difficult. So showing some of the results where we've done very careful tests to eliminate these grip failures, then you can see that we have these size effects. So this is showing some results from some tests some years ago where we had UD IM78552 with chamfered plies, and we had some small coupons, and then we doubled up all the dimensions, the thickness, the width, and the length. So we go over a factor of 8 in terms of linear dimension, with a factor of 512 in volume. And you see that there is a significant reduction in the strength from about 2,800 megapascals for the smaller specimen down to about 2,400 megapascals for the largest. And if you plot that as a viable distribution with a log-log plot, then the viable model seems to fit the data quite well. And the viable modulus for that is about 41, which is a relatively high value, which reflects the fact that although there is variability, it's not that huge. We also did tests a long time ago on scaled flexural tests. These are glass epoxy specimens, where again, we changed all the dimensions, length, width, and thickness. And we also, with the same material, did some tests where we just changed the length. And you can see in this plot here, again, we plotted this as a viable plot, and you can see that the data fits on this straight line. And you can see here, we've got the 3 specimens which failed in bending with different sizes, and the reduction in failure strain as you increase the specimen size is captured there. Here we've got the 3 different length specimens, which also fall on this line, and then the fact that the bending specimens show higher strain to failure than the tensile tests because of the fact that in the bending test, you've only got a small volume of material which is subject to that maximum stress. Then they all seem to fit on that viable line. Recently, we've done some work on a new test method, which I think is really very, very promising, whereby we use hybrid specimens. So this came really as a byproduct of a lot of work we were doing on looking at hybrid composites. And in this case here, we've got a specimen with carbon fiber epoxy and glass fiber epoxy on the outside. So it might look like a sort of an in situ tab, but there's more to it than that, really, because this is not just providing a tab, it actually eliminates the stress concentration altogether. And the reason for that can be seen by doing an FE analysis. So if you do the FE analysis across this here, you'll find that actually the stress in the carbon is lower than the nominal stress. And then you have an increase here where you go into the tab. And the reason is that by equilibrium, the total load has to be the same across that cross-section. So you have a stress concentration here in the glass, and the stress in the carbon has to be actually lower. And as a result of that, you completely eliminate grip failures, and you can get a true gauge section failure, which is unaffected by the gripping condition. So I think this is very promising. We get consistent failure, and we get the failure in the middle. You can see the specimen here, that it's failed in the middle. When it fails, when the carbon fails, it then delaminates, and you can see the delamination spreading, and therefore the specimen changes color. And so we can see that we've got a real gauge section failure. And actually, we don't even have to put tabs on these. We can put them straight into the grips of the test machine. And we get significantly higher failure strain and lower variability. So in this case here, with this carbon epoxy, we get 1.86% strain compared to about 1.5% with a more conventional test. So this is, I think, a very promising way of doing improved testing. It's very easy because you don't have to tab the specimens. I guess the only drawback is you're measuring strain, failure, not stress. And also you do have to apply a small thermal strain correction, but it's not very large. So we applied this for looking at size effects. So we did these scale specimens where all those specimens are hybrids. So they've all got carbon in the middle and glass on the outside. And again, we've doubled all the dimensions, thickness, width, and length. We didn't use tabs on these. We just tested straight in the test machine. And we got consistent gauge section failures. And again, we got a result which fitted on a viable modulus, showing a reduction in strength as you increase the size, and in this case, a viable modulus of about 25. So this confirms the size effect, which is pretty well known. It's been reported for many, many years. And despite a large amount of research, people will still argue about this and say, well, there isn't really a size effect. Actually, I think that these tests here, where we can be really sure that we've eliminated the failure at the grips, and really have got gauge section failures, I think that confirms really that we have a size effect in these materials. So to summarize on the UD tensile testing, strength is a statistical quantity. You get a distribution of strength really, rather than a single value. And therefore, it depends on the volume of material that you test. A viable model seems to fit the data, but there's still some questions about that. It doesn't necessarily fully answer all the questions, even though the data I've shown seems to fit it quite well. But then there's another question, is do we want to have strength values that are dependent on the theory? I could quote a viable mean strength, a viable characteristic strength, and a viable modulus, but do we want to have values which actually depend on the theory, which may not be fully accepted? And I think that the answer to that is probably no. So I think the key to this is that when we do carry out tests, we must specify the volume. Or maybe we should be having a range of standard volumes which will allow comparisons between different materials, but without necessarily having to get into the details of the theory that backs it up. Now that we do have better methods available, then I think we should undertake further well-controlled tests to really look at these things in more detail based on really sound experimental methods. So does the strength really follow the viable distribution? And another question which I would like to answer, which has not been fully really decided, is when we change the volume, is the effect of changing the length the same as changing the area? In these specimens, we scaled all the dimensions, but it'd be quite interesting to do some further tests to look at those independently. We then go on to look at what about the effect of other stress components. And here, these results to me were quite surprising when we got them. So we wanted to use these test methods with good gauge section failures to look at the effect of other stress components. So in this case, we've got interaction of shear and tensile stress. So in this case here, what we've done is we put angle ply specimens, angle ply carbon in the middle here, and then use the glass on the outside. So the glass has got the same purpose of avoiding failure where we grip them, so we can get gauge section failures, but by using angle plies, we can get combinations of shear stress and tensile stress. And because we're using very thin plies, these are only 0.03 millimeters thick, because they're very thin, then we suppress shear cracks and free edge delamination, which might be a problem with conventional angle ply laminates. And we did indeed get gauge section failures uninfluenced by other failure modes. So this high strength carbon epoxy, we tested plus or minus 5, 10, 15, 20, and 25 degrees. And you see that as you increase the angle, the shear stress increases significantly. The transverse tensile stress is pretty low. And if you look at the failure strain, you find that actually there's hardly any difference. These results up here show that up to 2% shear strain, we have really hardly any effect on the tensile failure strain. And only at this very highest value here, we perhaps see a little bit of a reduction. So the fiber direction tensile failure strain seems to be not significantly affected by shear. And in a multi-directional laminate, you're never going to get up to as high a strain as this before you get failure in other plies. So these matrix-dominated stresses don't seem to have very much effect. And the same thing happens in transverse compression. So we used another variation on a similar sort of approach, using thin carbon angle plies to induce transverse compression in UD plies in the middle. So here we've got UD plies in the middle, we've got angle plies on the outside, and because of the scissoring action of those angle plies, they put transverse compression across the width of the specimen. We can induce quite high levels of transverse compression by varying the angle on those specimens. And in this case here, those lower modulus angle plies, although they're carbon now, they still have a similar function in that they shield the zero plies from the stress concentration at the grips. So again, we get gauge section failures rather than failure at the grips. And we've done this with plus or minus 15, 20, and 28 degree laminates. In fact, the plus or minus 15, we did get some grip failures, so we had to put some glass on those as well, but the others were just carbon, all carbon laminates. And we did indeed get all gauge section failures. And what you can see here is that the failure strain in the fiber direction is hardly at all affected by the transverse compression. So we've got very large transverse compression up to almost 3% here, and yet the failure strain is hardly changed at all. And again, in practice, you wouldn't really be able to get beyond that. Otherwise, you would have failure in a 90-degree ply. If you had a typical quasi-isotropic laminate, you get failure in the compression direction in the 90-degree plies. And the compression here is quite high. We're getting up to 150 megapascals in the transverse compression, and it's still not having a significant effect. So coming on to laminate strength then, laminate strength is really not a material property. So I think we have to be very careful about talking about the strength of a laminate because it depends on many factors. So the first thing here is the effect of layup. So this is showing some results where we did it on quasi-isotropic iron 78552. All these results I'm showing here on this graph are all quasi-isotropic. They're all 4590 minus 450 layups. And the difference is in the thickness and the stacking sequence. So we have these first three here are dispersed plies where we repeat the sublaminate through the thickness. And these ones here are block plies where we block up the plies of the different orientations together. And you can see there's a large difference in these tensile strengths of these different laminates. And the reason for this is because we're getting premature failure due to delamination. If we look at the failure mechanism, what happens is we get matrix cracking, particularly in that surface 45-degree ply, and that leads to delamination from the edge. So if you look at this specimen here, and this is not the failure, this was taken away. You take a specimen which has failed, and then you look at the edge a long way away from it, then what you see is you have these 45 cracks on the surface, and then the delamination, which is a starting between the 45 and the 90, and then that propagates through the thickness. So when the plies are dispersed, that early delamination and transverse cracking results in premature fiber failure. When, on the other hand, you block those plies together, then actually that leads to a global delamination and the whole specimen failure by delamination. But in both cases, you see a reduction because the failure is starting at the edge and from those transverse cracks. So looking at that specimen, it looks like a gauge section failure. You see most of the failures at the edge, but my colleague Xiaodong Xu was working on the quasi-isotropic strengths, and he was skeptical about these results, so he went and dug out all these specimens out and noticed that actually, although it appears to be a gauge section failure, that 45-degree crack is starting at the tap. And one of the other things I showed on this graph here is that actually none of those specimens have reached the strength you'd expect on the basis of the unidirectional strength. So they're all below that failure because they've started prematurely. So when Xiaodong noticed these cracks here, he decided to repeat the tests, this time without any tabs and using a very gently chamfered grip faces in the test machine. And with this test method, he was able to eliminate these cracks initiating from the tab and managed to get the full strength. And so what we found was the strength of the quasi-isotropic did indeed match the strength you'd expect on the basis of the UD plies themselves, so long as the volume of the UD plies was taken into account. So what this shows is that the laminate and the 0 degree strength can be reconciled, provided you eliminate the failure prematurely, and also provided you take into account the volume of the 0 degree plies. Another factor which is not really well understood is constraint from adjacent plies. What we've shown is that very thin carbon plies can show higher failure strain by quite a significant margin. In this case here, I'm plotting here some data from hybrids. So here we've got carbon plies sandwiched between UD glass. And what you see is that as the carbon becomes very thin, the failure strain increases, and it's not a small amount. The failure in this specimen here is 1.86% for the thicker plies. But as you get down to this ply here, which is only 0.03 millimeters thick, we've got 2.23% strain. There's a 20% increase in the failure strain over the baseline. Quite a large effect. And the reason for this, we believe, is because of the constraint on forming the critical clusters of fiber breaks, which can form the failure. So in the limit here, if you consider a specimen which has only got one layer of carbon fibers, when these carbon fibers break, then if these ones are glass, then there are no fibers there for them to connect up with. So it's more difficult. They have to break these ones here. Whereas in a cluster of carbon fibers here, there's more fibers that they can link up with. And so it's easier to form a critical cluster. So in these thin plies, we have a constraint on that cluster formation, and hence we see an increase in the failure strain. So in this study here, Thomas Rev did some cross-ply specimens. And in all these specimens, we've got 0 degree plies in the middle here. And then next to it, we've got some 90 plies. And then we need some other plies and some glass to avoid the grip failure. And what he did in this study was to vary the thickness of this 90 degree ply, which is next to the 0 degree carbon. And what you see here is the longitudinal failure strain, the tension strain, as a function of this 90 degree ply thickness. Baseline is up here, about 1.65% for this material. And all these results are slightly reduced. And perhaps what's more surprising about this to me is that these ones here are very thin, and actually the transverse cracking was largely suppressed. These thicker ones here, we've got definite transverse cracks, but all of them actually showed a small decrease in the failure strain. So I think this is still an area which needs a bit of further work, because this is slightly inconsistent with what I was showing before. I showed with the quasi-isotropic laminates that we could reconcile the 0 degree strength with the quasi-isotropic strength. But in this case, we're showing that actually the cross-ply strength, the carbon fibers are a little bit weaker than they are in the unidirectional. And this may be to do with the fact that in this case, the 90 degree plies are directly adjacent to the zeros, whereas in the previous one I showed there was 45 plies next to the zeros. So even if there were cracks in the 90s, they may not have affected the zeros to the same degree. But I think this needs some further work to better understand. So the summary then on the laminate tensile testing, laminates may fail prematurely due to transverse cracks and delamination, and this depends on the stacking sequence and the ply thickness. We can reconcile UD and laminate strength, provided we avoid premature failure, and also provided we take into account the volume of the 0 degree plies. Other stress components do not seem to have a significant effect. This is perhaps a little bit surprising, but on the other hand, when you consider that the tensile failure mechanism is dominated by the strength of the fibers, although the matrix plays a role in transferring load, perhaps it's not so surprising that stresses transverse to the fibers don't have such a large effect. We've also seen that constraint from adjacent plies can increase the failure strain, and that transverse cracks may reduce the failure strain. But I think the big message from this is laminate strength is not a material property, because it depends on many other factors. So that's tension, but what about compression? Well, actually, compression is even harder. With normal direct compression tests, you can't really avoid stress concentrations or the effect of other stress components. Some FE analysis I did many years ago, we showed how the stresses were higher near the tab, and how we had these very high shear stresses, which are known to be detrimental in compression. So it's not surprising that we get premature failure. What about flexural tests? Well, by using 4-point bend tests like this, we can avoid grip failure. And in many composites, we do get compressive failure in this sort of test, not in all composites, and that could be a whole other talk as to why, but in some composites, despite the fact that generally composites are supposed to be stronger in tension than in compression, in some composites, actually, you see tensile failure in these bending tests. But if you do those tests carefully and you use large enough rollers, then you can get gauge section failures in these flexural tests. Alternatively, we did tests some time ago using this pin-end buckling rig, which eliminates any issues about local contact or roller contact stresses completely. We did some scale tests on those pin-end buckling tests, where the whole thing was scaled, length, width, thickness of the specimen, and indeed the end fixtures. And what you see is a very large effect, with the strain varying from about 2.1% on the very thin 1 millimeter specimens down to 1.5% on these thicker specimens. So quite a significant effect of the size of the specimen on the compressive failure strain. And really, in this case here, failure is due to a shear instability at the micromechanical level. And what we think is happening here is a strain gradient effect, and the fibers which are less stressed away from the surface support the other more stressed ones and therefore inhibit the instability failure. So whilst we think this is largely effective of strain gradient, then you've also, by changing the strain gradient, changing the specimen dimensions, you're also changing the volume of stress material. So we can't really separate those two effects in these tests. So in order to overcome that, James Atkinson developed this constrained buckling test rig where the specimen is clamped and we can adjust the initial angle and the additional offset so that we can actually get different combinations of compression and bending. So these results are with the same T800-924 material as in the previous pin-ended buckling, and all these specimens are similar sort of size. They're not exactly similar, and in particular, they are all same 2 millimeter thickness. And you can see that there is a variation here, with as this strain gradient increases, that failure strain increases as well. And so this demonstrates that the effect of the strain gradient is there independent of the volume of the specimen. More recently, Shun Wu's developed this carbon wood sandwich beam, which is a very nice test method, and I think, again, we're going to use this quite a lot in the future. And in this case here, you've got carbon fiber skins, top and bottom, bonded to a wood core. Wood is very good because it's got a high shear strength and it supports the carbon very well, so you don't get any failures locally influenced by, for example, by the use of honeycomb core. There are issues to do with localized stresses at the core. So this seems to do a pretty good job. And provided you use large enough rollers, you can avoid local failures and get a good compressive failure with this type of test. So if you look at the results for that, this is for IM78552, where the skins are 0.5 millimeter thick. This is the slide here. Let me just show you what we've done here to vary the strain gradient. So the depth of the beam can be changed independently. So when we change the depth of the beam, we can keep the distance between the rollers and the width the same. And so the volume of material is the same, but we've got a different strain gradient. And we also have to increase the span in order to limit the loading forces and prevent a localized failure. By doing that, then, we can test with the same volume of material, we can look at what the effect of that strain gradient is. And what you see here for these 0.5 millimeter skins, the core varying from 6 to 38 millimeters thick, you can see that at these very low levels, the strain is increasing substantially. But once we get up past about 10 millimeters, there's not really very much effect. And so these values here, I think, are representing real compressive failure rather than an artificially high one that we get due to the suppression due to the strain gradient when the specimens are thinner. And that value there of 1.36% strain, I think that's about the highest value I've seen for compressive failure. And the other ones I've seen are 1.2% is about the highest other one I've seen in direct compression. So it's significantly higher. And I would say that this is probably the best value for this material because we've eliminated the stress concentrations and we've also got a deep enough specimen to avoid a strain gradient effect. So I think this sort of testing gives us a real opportunity to understand a bit better what happens in compression failure and how it depends on various factors. So the effective ply thickness, that's another thing which makes a difference. So you can see these tests here done at EPFL with different thickness plies. You can see the very thin ones down to 30 grams per square meter, significantly stronger, and also lower variability in strength. And this is because there's greater homogeneity. Those micrographs, you can see that this one with the thin plies on the right is much more homogeneous. With the thicker plies, you see more resin-rich regions between toes. And so this shows a more general issue, which is that the manufacturing process may affect the distribution of fibers, the microstructure, fiber alignment, and hence potentially the compressive strength. Other stress components, well, I think it's well known that shear stress significantly interacts with compressive strength, and these results from Cambridge from a long time ago with combined torsion and compression on tubes show very nicely the approximately linear interaction between compression and shear. But the interaction of other stress components is much less clear. I think we need better tests to try and get to the bottom of that. So a summary on the compression testing. The direct compression tests underestimate the strength. Flexural tests can overcome premature failure, but the strain gradient can have a very large effect, so we have to be a bit careful there. But with flexural tests with large rollers and sufficient depth to overcome that strain gradient effect can give satisfactory results. The shear stresses have a big effect, but there's other components that are not so clear. And what I think we should do now is to use these state-of-the-art test methods, such as this bending I've just shown with the sandwich specimen, to really look at some of these things in more detail. What is the effect of the stress volume independent of the gradient? What about the effect of other stress components? What about constraint from other plies and stacking sequence effects? So far, we haven't really been able to look at these because of difficulties with the test methods. So, in conclusion then, why do we see such a large variation in reported strengths? Part of it may be due to a lack of a consistent definition of strength. There's certainly intrinsic variability in effect of manufacturing processes. We have a lot of poor test methods and variations in how tests are carried out. But also, we have other factors, such as that UD strength depends on stress volume and the strain gradient. And laminate strength is really not a material property at all. It depends on many factors due to the interaction of different failure modes. So in terms of some implications from this, I think one thing is I think we should be more critical about experimental methods and data. I think there's a lot of work done where people perhaps don't look at that carefully enough. I think it's really important. And in particular, we shouldn't assume that if we get a correlation between models and tests, that this means that they're correct. I think we should use a consistent definition of strength, and the suggestion here is we use the maximum stress that a unidirectional composite can sustain under uniform uniaxial loading. When we do report values, we should state the conditions under which they were measured and the volume of material. And we should recognize that laminate strengths are not material properties, and I would prefer to refer to those as failure stresses rather than strengths. Might seem a fairly subtle distinction, but I would prefer to keep strength to the ultimate material parameter and use failure stresses for cases where we have so-called strengths which actually depend on the configuration. And what's the way forward? Well, I think there's a real need to synthesize the huge amount of work that's been done, particularly on testing methods, so we can reach a consensus on what are the best methods and what should we do and what shouldn't we do. What is it that we do fully understand and can agree on? And what are the things that we don't understand and where we need to do more research? And what I would like to see is reaching some consensus on this and having collaborative programs where we can really systematically address these critical issues so we can really start to make some progress on understanding these complex issues. So the way to take this forward, we had this workshop about a month ago on the definition of strength, and our proposal is to organize a series of workshops on each of the primary failure mechanisms, starting probably with fiber direction tensile strength, but also looking at the other failure mechanisms, and trying to reach more of a consensus on what we understand, what we don't understand, and putting in place some further research to really address the challenges that are still remaining. So with that, I'd like to thank you. There are references in this paper, which I will make the PDF will be available. And with that, I thank you for your attention.
We thank Professor Wisnom for his presentation. My name is Jonathan Goodsell, and I'll be fielding questions here. And so, Professor Wisnom, the first question we have goes back to the volume and size effects. And says you've shown clearly that there are volume and size effects. And fundamentally, the question is, why do these effects occur?
So the effect is really, for the tension case, it's because the failure of individual carbon fibers is defect controlled. If you take individual carbon fibers, there's huge variability in the strength of those fibers. And when you translate that into a composite, the strength depends on not just single carbon fibers, but still depends on clusters of weak fibers. And so that because the strength of individual fibers is defect controlled, the strength of the composite is also defect controlled, but it's really these clusters of weak fibers which will depend on the volume material. The larger volume material, the more likely you are to get a weak cluster of fibers close together.
As a follow-on to that question, someone asked, as we look at these size effects, is there a size at which the effect stops? So would there be, could you get a specimen so large that you don't see these size effects anymore?
Well, I think that's a really good question. And I don't know the answer to that. I think we would need to do more testing. There have been some indications that perhaps that might be the case. But my experience with size effects is that always you need to test a bigger specimen. So any time we've done these size effects, we always end up saying at the end of it, oh, well, we'll just test one more bigger specimen and then we'll know. And but we've never got to the point of testing one big enough. So I suspect that they will continue to go down with higher levels. The rate at which they decline may change. And there were some indications many years ago, there was some tests done on large scale rocket boosters, which were really large structures. And there were some indications that perhaps the size effect was less at that scale. But I think the jury's out at the moment. And that's something I would really like to find out about.
Well, I think that then feeds into another question, which had to do with large scale structures, asking the question around defects, volume, and load introduction, where how do we scale these very precise and detailed and even size dependent findings up to large scale structures where there could be the load introduction is not so precisely controlled, and we're often dealing with larger structural sizes than in these test specimens.
So I think there's several different parts to that question, I guess. So I think it's really important that we understand the fundamentals of how composites behave, and I think it's really important to know how it depends on volume, how it depends on stress components and these effects. Now, if you're designing a practical structure, you might be more interested in just having some conservative value you can apply fairly straightforwardly without worrying about some of these effects. And if we have a solid understanding, we can come up with criteria which enable us to do that. But going back a while, one of the first UK test standards for tensile strength, one of the industrial partners complained that the results gave too high values. So they didn't like it because they were too high and they didn't match what they obtained in the real structures. So that was, I believe, was a good test method, but in the real structures, there were other confounding effects which were tending to reduce it. So what I think we should do is we should really understand what those effects are, and therefore we can have a rational basis for reducing those strengths, if we need to come up with design allowables. So that will be my approach. I would hope that we can understand this better, so then this will feed into reliable failure criteria, which we can then use in conjunction with finite element or other analysis methods to find out what the stress distribution is in the part, and on that basis make reliable strength predictions. But we're still some way off from doing that at the moment.
So you mentioned test standards, and someone asked the question around what implications do your findings have for the way that we we write these test standards among the different bodies and how we design these standardized characterization tests?
So I think that's another good question. I would be quite interested to interact a bit more with some of those bodies. I think there's a lot of really good work been done on the test standards. I didn't mean in any way to denigrate that. I think it's very difficult to come up with test standards, but test standards really are about consistency and reproducibility rather than necessarily about actually getting the ultimate value out of it. So there may be a different objective there. But I think that these findings have shown some of the issues which need to be taken into account. Sometimes the standards don't include all the factors which may affect things, and I think that that's something that needs to be done.
Talking about those factors, someone asked a question along the lines of temperature effects, loading rate effects, and so on. Do you have any comment, and certainly you've done lots and lots of testing along those ranges, do you have any comments or generalizations you would make about rate effects or temperature effects or other effects in testing and strength?
Well, of course, those are very good questions. They certainly do have effects, particularly in compression. So I would say that the compression shows more rate and temperature effect. Tensile strength is generally not so affected by those effects because it's fiber dominated, but in compression in particular, I guess the hot-wet is usually the worst one for compression because you get a lot of degradation in the matrix support in those conditions. So that's definitely very important. But also rate effects are important in compression as well because, again, it's matrix dominated and the rate effect does affect the matrix performance. So you definitely need to be aware of those and to make sure that your test results are consistent with how you want to use them.
As we start looking more broadly, people are raising the questions around discontinuous fiber composites, and perhaps you could comment briefly on what findings and what generalizations you would draw here from this work on continuous fiber composites. What is similar and what is different as we start looking into the world of discontinuous fiber composites? And I think people are particularly thinking about strength of those systems.
Well, so that would be a topic for a whole other talk, I think. That's a big question, and we have done a lot of work on discontinuous composites, and I think as far as the testing is concerned, I think the findings are really quite similar. You've just got to be careful with your tests, and the same sorts of factors affect it as they do with the continuous materials. With discontinuous, you've got additional mechanisms that come into play where you can actually have the individual fibers interacting. So you've got an additional failure mechanism. If you're talking about really well hybridized, very well mixed materials, then I think the behavior can be very, very good. If you're talking about more chopped prepreg and things at that level, then clearly you have scope for localized delaminations and failure between the platelets. So that can give you additional failure mechanisms, which clearly need to take account of.
So someone in the questions is trying to look ahead into the world of simulation and understanding where predictive simulation might go, suggesting perhaps the idea of virtual design allowables and so on, micromechanical prediction of these properties. Do you have a comment on that, the ability to go from the constituents up to the strength of lamina and laminates?
Well, I think that's really critical, and that's the holy grail. That's what we want to do, and I think we're making a lot of progress on that. We've demonstrated that you can go from ply level properties up to the strength of quasi-isotropic specimens with holes, and even recently looking at predicting the R curve in fracture on quasi-isotropic laminates. So I think we're making a lot of progress, although there's still some areas which are not fully captured. I think that going from the micromechanical level, I think there's still more work needed. I started in that work when I first started on composites with that ambition to go from fiber and matrix properties, but we found a lot of issues, and I think there's still a lot of issues to be addressed before we can go from basic fiber and matrix values all the way up to structural strength predictions. But that's clearly where we want to go.
Mm-hmm. Can you comment even further? Someone raised a question around toughness, and is there any evidence of relationship between strength and toughness, and do any of the findings that you've discovered have any bearing on toughness or perhaps other kinds of performance properties in addition to the strength of the composite.
So toughness of a composite, we're talking about fiber fracture toughness, that rather than delamination toughness. It clearly does depend on the same sorts of parameters, and it's pretty complex. We've done quite a lot of work on that, and I think we've got quite some understanding of that, and it all depends on the local failure. If you have a crack or local stress concentration, you get a very complex damage sequence around there with cracks and delaminations and localized fiber failure. And what we have to do in order to be able to predict that effect is to be able to take account of those localized damage mechanisms and the effect they have on the overall performance. So we've done a lot of modeling work on that as well as experimental work. I think it's a very interesting topic. But again, it's probably subject for a whole nother talk.
Well, that's a good note here to conclude on. Professor Wisnom, we appreciate your talk today and look forward to continuing to learn with you and from you in the future. And thank you again, both to all of our participants, our sponsors, those who've asked questions. Professor Wisnom, thank you for fielding these questions and for this talk.